Okay, good morning. So we have been discussing about flow regimes from the previous class, and in particular, I have discussed about flow regimes in liquid gas horizontal pipeline and the solid liquid horizontal pipeline. Now, we'll be quickly discussing about gas solid flow regimes in a horizontal pipeline. So typically these flow schematic representation are shown with the one important characteristic curve of the gas pipeline, which is pressure drop versus gas velocity. Okay, so typically from our understanding of fundamental fluid mechanics, we know that if we have delta p pressure and say if we have fluid velocity over here along abscissa and pressure drop along this line. So in case of single phase flow inside the pipeline, we have two types of regime. One is laminar flow regime and other one is turbulent flow regime. Okay, and if we see these pressure drop characteristics, we know that initially at low velocities, when velocities are less than the critical Reynolds number at which transition happens from laminar to turbulent flow, our pressure drop varies in a linear fashion with velocity. Okay, so delta P is directly proportional to velocity for laminar flow. Whereas when we go away from this, then typically it follows some curve, and after that this curve follows a relation of delta P proportional to V power 1.75, and where it follows this relation of V power 1.75, this is our turbulent flow. And in between this, where curve changes from linear relation to this proportionality of 1.75, here comes our transition regime or transition flow. Is this one clear? So this is the pressure drop versus velocity characteristics for a single phase flow. Now, in this gas solid flow, what we are doing, here also we are having a fast moving gas, and in this fast moving gas we have also loaded the solid particles. Okay, so that is the reason it is becoming the gas solid flow. Now, here if you see, in this particular regime, you will find that the nature of the curve will be almost close to this one. Okay, because in this regime what we have, velocities are very high and all the particles are dispersely present in the gaseous phase. Okay, so in this scenario we will be having very high speed gas or high velocity gas. Okay, so once you have high velocity gas, then the interaction force because of the gas on particles will be such that all the particles will remain suspended in the gas, and moreover if amount of gas is very high, flow rate of gas is very high and solid mass flow rate is less, then particles will also be sparsely placed in the pipeline. Okay, so these will not be close to each other. So this type of flow is called as dispersed flow. Okay, and here you will be finding that the behavior of the pressure drop will be almost like our turbulent flow characteristics. Now when we decrease the velocity, what will happen? If I keep the solid loading same, like mass flow rate of solid which is put inside this pipeline, that is the same, but only I have decreased the gas velocity. So if I decrease the gas velocity, what will happen? Of course, the relative velocity between the gas and solid may decrease. Okay, and ultimately you will also find that settling of particles will start near the bottom. So once settling of particles is starting near the bottom, we call this as moving cluster flow. But in this case also, here you can see that the bed of the bottom portion, or I can say this particular bed of the particle, cluster of the particle, it is not settled, it is still moving at the high velocity as that of the gas. Okay, When I further decrease the velocity, then what will be happening? If I further decrease velocity, more particles will be settling, and we will be finding that settling bed plus particles are actually co-flowing together. Okay. Now after this point comes the important thing. So up to this point, almost the pressure drop and velocity, gas velocity characteristics are actually identical. Okay. But after this point, before this point, what is happening in this particular regime? If I further decrease the velocity, pressure drop has started increasing. On contrary, if you talk about single phase flow, when you further decrease the velocity, ultimately your flow regime enters into the laminar flow regime and your pressure drop linearly decreases. Okay, but here situation is different. Why so? Because after this point, when you will further decrease the velocity, you will be finding now the mass flow rate of the gas is less in comparison or comparable to that of mass flow rate of the solid, and mostly these solid and gas are occupying almost the same volume fraction of the pipeline. Okay, and in this case we will be finding at the bottom very closely spaced layer of particles will be settling, which I can call stratified flow. Okay, now in the stratified flow, what will be happening? In this top region there will be slightly higher velocity, in the bottom region there will be lesser velocity. Okay, so solid will be moving at slightly lesser speed in comparison to the gas. And here you can also find that something, this much portion is filled with the solid and this much portion is filled with gas. Now when you have to calculate the wall shear stress, then for this top portion you have to consider the viscosity of the gas, but in bottom portion solids friction will be coming into picture, because solid particles are very close to each other and these are kind of sliding over the surface. Okay, so this solid friction typically will be significantly higher in comparison to the friction because of the surrounding gaseous phase. So that is why we will be finding that significant increase in the pressure drop will be observed. Okay, and further decreasing the gas phase velocity will keep this undulated solid layer, which is called as unstratified flow, and finally if further decrease the velocity, you will be finding that these solid particles are almost touching the top boundary, and in between gas pockets are there which are moving in the forward direction, and these are pushing these solid boundaries. Okay, and if you further decrease the velocity before that, then ultimately what will be happening? Almost your entire pipe will get filled with solid. Gas amount will be very minimal in between the interparticle void spaces, and ultimately your flow will be choking. So it will almost reach to a choking situation. After that, if you have to again start the flow, either you have to first stop solid and over here pass the over pressurized air. If that is also not able to make the flow happen in the pipeline, then ultimate job is open the pipeline and take out the solid and then again make the flow happen. Okay, so this situation is situation of choking. Now typically what happens, this is the point where settling is actually starting at the significant level. Okay, so above this point, when your gaseous flow rate is significantly high in comparison to liquid flow rate and in comparison to solid flow rate, and the solids are present in the less fraction, this type of flow is called as dilute phase flow. Okay, because here these are present in the less, solids are present in the less concentration, and here when these velocities are in such a way so that the solid fraction is more, this type of flow comes under the category of dense phase flow. So first important point is this pneumatic transport of fine powders is actually because of its high pressure drop characteristics, it consumes significantly amount of high energy in comparison to the other mode of transportations such as the belt conveyor and the bucket elevators, etc. Okay, but still this mode is preferred in industry, particularly for transporting the fine powders, because if you use the belt conveyor, etc., for transporting the fly ash or say cement or other type of fine particles, then you will be finding that these may lead to significant amount of environmental pollution. Okay, because fine particles, if say you say that belt conveyor is actually moving and in that belt conveyor you have loaded the fly ash particle. Once wind will be blowing, what will happen? That will try to carry significant amount of particles, fine particles with it. Okay, so though the belt conveyor or other modes which particularly have interaction of particles with the surrounding atmosphere, these may consume less energy in comparison to this type of transport of solid particles inside a pipeline using pressurized gas, but these are not good for environment. So that's why majorly in the industrial system for transporting fine solid particles, pneumatic conveying pipeline is used. Okay, but the reason, as I already told you, if we operate in dilute phase flow, then still it is having less pressure drop in comparison to the dense phase flow. But majorly whenever we operate in the industry, we want to operate our system in dense phase flow. What is the reason? The reason is, if we operate in dilute phase flow, what will happen? Velocity of gas and particles will be very high. Okay, so when high velocity solid particles will be striking with the wall, and when these will be like this striking with the wall, ultimately what these will do? These will actually lead to erosion of the pipeline. Okay, so high momentum of particle, whenever it is striking with the wall of the pipe, this leads to erosion of the pipeline. So because of this, your pipeline failure will be taking place at the faster pace. On the other hand, if I operate in this regime, though my pumping power is slightly high, but wear of the pipeline will be actually less. So typically this type of thing is preferred, and I have already told you why there is difference from the single phase flow characteristics, because in this scenario, whenever we are calculating the friction, it is combination of friction because of gas plus friction because of the solid. In single phase flow, whenever you operate, you do not have any solid present. Okay. Now let us talk about flow regime maps for vertical pipe flow. So whenever we started the discussion on flow regime map, I told you yesterday that these also depend upon the orientation of the pipe. Okay, so now you will be finding that when orientation of pipe is changed from horizontal to vertical, typically for gas liquid flow, many flow regimes which were present in horizontal pipeline, these are now not present over here. Okay, so one such regime can be stratified flow. So in case of stratified flow, we saw that in horizontal pipeline, heavier fluid was settling at the bottom and the lighter was at the top. Okay, but whenever you will be finding that in a vertical pipeline, two fluids are co-flowing together, then this type of stratification will not be possible. Okay, because the inertia of the fluids has to be sufficient enough in order to push both the fluids in upward direction. On contrary, if you decrease the velocities in such a way so that their inertia becomes very small in comparison to the gravitational forces, then you will be having stratification, but ultimately in that scenario flow will not be possible. Okay, so their heavier fluid will settle at the bottom and top will be at the lighter will be at the top, but ultimately flow will not happen. Okay, so let us talk about the flow regime map for air water flow in a vertical tube of 2.5 centimeter diameter, and this is again under the adiabatic flow conditions. Okay, so here if you see, one regime is shown which is typically observed when liquid volume fraction is high or liquid volumetric flux is high and gas volumetric flux is low. So in this reason, gas velocities are less in comparison to the liquid velocity. Okay, so what will happen? Of course, the fluid which is present in more quantity, that will be behaving like a continuous phase. Okay, so here liquid will be behaving like a continuous phase, and when these small dots are there, these dots are nothing but bubbles. Okay, and this is called as our bubbly flow regime. Okay, and moreover, in this regime gas velocities are so small that these bubbles are also having sufficient distances between them. Okay, when you increase the gas phase velocity keeping the liquid phase velocity almost the same, what happens? More amount of gas will be coming. If more amount of gas is coming, instead of occupying only this much space, it will now occupy more space. So while it is occupying the more space, all the bubbles which are close to each other, these are forming a single entity. Okay, and this single entity takes this particular shape. So here our gas is there, and when we know that when flow happens across a solid object, what happens? At high speed, near the back end, we have this type of recirculation pattern formation in the wake of the solid body. Okay, so similar situation will be here. When this gas is penetrating in upward direction inside the tube, there can be formation of recirculation structure behind this one. Okay, so these recirculating structures, what these will do, these will lead to the occurrence of dynamic interface at this point, and from this interfacial waves will be there, and if the amplitude of any wave is growing, that will lead to formation of one small bubble at the wake of this bigger bubble. Okay, so the small bubbles which are traveling behind this, these are called as satellite bubbles.
Sir, in this checking phenomena भी also
Sorry?
sir checking phenomena जो होता है वो इसी में अगर
No, not here. This is adiabatic flow. So that type of instability comes when we talk about condensation of steam in subcooled water. Okay, so this will not happen here. Then we have churn flow. Okay, so when we slightly increase the gas flow rate, then this frequency of slugs will be increasing, and multiple slugs, when these are joining together, these may lead to random fluidic behavior and formation of instability, which will be leading to very chaotic flow regime called as churn flow regime. Okay, and further increasing the gas velocities, what these will do, these will create the gas fraction, or gas fraction will become so high that entire core of the pipe will be filled with purely the gas. Okay, so now in the core of the pipe gas is moving, and in the outer side our liquid is moving. Okay, so here you will be finding that this liquid film typically has low velocity in comparison to the fast moving gas which is going through the core. Okay, and whenever this gas is moving at high speed, any perturbation which is there at the surface of the pipe, that perturbation, if reaches the critical regime, if it grows further, then it may increase, there may be growth in its amplitude, and one lamella of liquid will be generated, which will be then finally pinching off in the form of small droplets. So typically in the annular flow regime, we are having combination of both, combination of liquid and gas, and inside the gaseous core there will be presence of large number of droplets. Okay, so whenever we talk about heat transfer, in heat transfer, particularly in boilers etc., whenever in the boiler tube near the end portion we have significant amount of vapor fraction present in the tube, then we typically observe this type of annular flow. Okay, and one regime is shown over here which is called as dispersed flow regime. So typically when liquid flow rate is extremely high, then what will be happening? For any gaseous flow rate, we will be finding large number of infinitely small bubbles are present in the system, and that will be making the situation as completely dispersed flow. So these are some photographs. So here you can see when air water flow is observed in a 25.4 mm diameter pipeline. So this is a 1-inch diameter pipeline. So here you can see in the bubbly flow regime, these are the different bubbles which are actually moving upward. And then you can see the slug flow regime. This is our slug bubble, and in the wake of the slug there is formation of strong vortices which is leading to formation of small bubbles, and behind that also we have large number of bubbles present. Okay, then this is the regime where the slug length has increased significantly. If you further increase the gas flow rate, what will happen? The length of the slug will be very high, and behind the slug you have large number of cluster of bubbles present. Okay, because if bigger is the slug, the recirculation zone behind the bubble will be also bigger. So because of that, the cluster of bubbles which is present behind this slug, that will be actually significantly high in number. And ultimately, which regime will be coming? When these multiple slugs will be merging together, these will lead to formation of instabilities at the interface, and we will be having very chaotic flow regime which we call as churn flow regime. Okay, once we have bypassed the churn flow regime, then we will be mostly entering into the annular flow regime. So in annular flow regime, here you can see this is actually a thin film, and in this thin film you have so many wavy patterns. Okay, so this interface between the liquid film and the gas is not smooth, it is having many wavy patterns. Okay, and these waves, depending upon their amplitude, when they grow, they extend the liquid lamella into the gas, and this fast moving gas then break this lamella in the form of small droplets. Okay, so at the center, whatever you are finding, these are the liquid droplets which are present in the gaseous core. While I have schematically shown you, in schematic representation, this was clearly looking something like this. But when we are seeing in the experimental photograph, it is showing us large number of bubbles. One reason for this could be the camera with which we are recording this. If the depth of field of the camera is actually large, then it will not be giving a single sectional plane, rather it will try to show us the multiple planes of finite thickness. Okay, so depth of field means, say this is the zone where you are, this is the zone where you are focusing. Okay, so if your depth of field of the camera is very fine, then it will be, your camera will be focusing in this zone only, say in the zone of 1 micrometer. But if depth of field is high, then it may focus on say 1 millimeter area. So if you are focusing in 1 millimeter area, it means that all the phenomenon which are happening in that band of 1 millimeter, all your camera is actually capturing. Okay, so if depth of field is large, then you will not be able to focus on a single plane. You will be finding that multiple planes of finite thickness are, or a volume of finite thickness you are actually visualizing, and in that way all the things which are happening in that, these will be actually we will be observing. So what will happen? It may happen that in one plane I only have these bubbles, in second plane I only have say these many bubbles. If my camera is focusing on both the planes, then ultimately what will be happening? All these will be combining together and I will be getting a single picture. Okay. So this is for slightly larger diameter pipe. So in this larger diameter pipe also you can see that bubble, then the initiation of the slug flow, then a larger slug, and then chaotic situation like churn, and finally the annular flow. And here you can see the film in larger diameter pipe is actually having large amplitude waves. So all these are actually the waves which have generated on the liquid film. Okay. So the previous flow regimes, what I described, these flow regimes were based on the superficial velocity. Okay. And in this flow regime now, momentum flux is actually shown, liquid and gas momentum flux. So the inclusion of liquid and gas momentum flux actually makes the situation slightly more generic. Okay, because ultimately if you only use the superficial velocities, then whatever the density ratio and viscosity ratios were used for a particular combination, if the fluids with similar density and viscosity ratios are available, then only you will be able to get the similar type of flow regime. Okay, but if you are slightly changing the densities and viscosities, then the previous regime may not give you the very accurate prediction. Okay, so that is the reason if we combine density and density along with the say volumetric flux, then ultimately we will be getting the mass flux or momentum flux. So over here we are plotting it with the momentum flux. Momentum flux means rho L into JL will be mass flux. If I further multiply it with JL, then I will be getting momentum flux. Okay. So Hewitt and Roberts, they have plotted this in terms of momentum flux of liquid and momentum flux of gas, and typically the regimes which we observed in the previous discussion, almost same set of regimes are observed, but only difference is this experiment is done in a 3.2 centimeter diameter tube, and again here both air and water are used, and this regime is also applicable for steam and water at high pressure conditions. Okay, and you can also see that how transition takes place when fraction of the air is actually changed. So in a single pipeline of 10.2 centimeter diameter, when 1% of air is present, then you can see the bubbles are actually sparsely spaced. When fraction of air is increased, then also we are in the bubbly flow regime only, but these are actually very closely spaced. And when the fraction is greater than 15%, then significant amount of portion of the bubble will be highly dispersed within the liquid medium. Okay. All are clear with this point? So whatever discussion we have done, that was for adiabatic regimes. Now let us briefly talk about the flow regimes inside the tube where actually phase change phenomenon is happening. I will be over here briefly discussing this at the moment, because as we have decided that in the module of special lectures we will be mostly talking about the phase change heat transfer. So while I will be starting the last module, then phase change heat transfer again we will be taking up in details. Okay, but for your understanding, if I simply consider that I am having steam water flow in a vertical boiler tube, then what happens? So typically at the bottom there can be entry of either saturated liquid or subcooled liquid. Is this point clear? So liquid can be either subcooled or saturated, but mostly if I am talking about the boiler tube, then in case of boiler tube it will always be saturated liquid. Okay, is this point clear? And whenever this liquid is entering, initially what will happen? This liquid will try to gain some heat. Okay, and the heat transfer will be because of which regime? Natural convection or flow convection? Because this is flowing inside the tube, so it will be because of flow convection. Okay, so whenever we talk about pool boiling, what happens? Here we see formation of bubbles. Okay, and whenever I draw the pool boiling curve, Q double dash and T wall minus T saturation, Then initially which regime we observe? This is our natural convection. Okay. And after that we observe which regime? Nucleate boiling. Okay. So here where formation of small bubbles start appearing at the surface, then we call this regime as nucleate boiling. Now one important point, you have to note it down. In this boiling curve we see that at the entry point degree of superheat is 0. It means wall temperature is equal to the saturation temperature. But when I slightly increase the wall temperature, and when wall temperature goes 5 to 10 degrees higher than the saturation temperature, then only the formation of the bubbles starts. Okay. So do you know what is the reason for that? What is the reason why? See, in thermodynamics what we study? In thermodynamics we study that if say this is my TS diagram, then if this is saturated liquid state, if I add heat, liquid will start getting converted into vapor, and at constant temperature I will be getting the vapors forming unless or until entire liquid has converted into vapor if I add the heat. Then temperature remains constant. Okay. But in reality, whenever we have plotted the boiling curve in the heat transfer, we observe that exactly when we add the heat at 100 degrees Celsius, the vapor bubbles does not form at this point. Vapor bubbles form after some point. So do you know the reason for this? What could be the reason for this? Maybe we will try to explore all these aspects whenever we will study phase change heat transfer. But as our understanding of pool boiling heat transfer says that from the boiling curve, if I even allow the saturated liquid to flow, it will not immediately form the bubbles. Okay, bubbles will be forming after there is slightly more increase in its temperature. So that is the reason initially when saturated liquid is entering the pipe, we will be having first, it is remaining purely in the liquid phase only, and we have convection regime over here. Okay. And after this, there will be formation of small bubbles. Okay. When these bubbles are coming into picture, then our flow will be becoming bubbly flow. Once the number of bubbles will keep on increasing, these will be forming the larger chunks, which is called as the slug flow. If I go further away, then multiple slugs will be joining together, and these will be forming a gaseous core. Okay. And outside the gaseous core, I will be having thin film of liquid, which is called as annular flow. And of course, this thin film of liquid, because of these interfacial waves, it will lead to formation of small droplets, liquid droplets into the gaseous core, which is moving at the center. Okay. And finally, when entire liquid has converted into vapor, then in this vapor I can have small liquid droplets present over here, which will be entering into the regime of dispersed flow, and at the end I will be getting the pure vapor. Okay. So you can see that if you simply control the flow rates in a adiabatic situation, then upon controlling the flow rates of the two fluids, your flow regime was remaining same, and that particular situation of flow regime, after leaving the entrance portion, almost in the entire pipe it remains the same. Okay. So it means that if you have an adiabatic flow pipeline, then and the length of the pipeline is significantly high, so that entrance effect can be negligible, whatever phase distribution you are getting, same phase distribution can be extended for the entire pipeline and analysis can be done. Okay. But if you are using a pipeline where the flow is not adiabatic, okay, phase change is also taking place. In that scenario, what will be happening? at different portions of the pipeline, the fraction of the liquid and vapor will be different. And this difference in their fraction will be leading to differences in the velocities as well as differences in the local velocity. From the bottom, you may be supplying same amount of liquid at the constant velocity, but ultimately what will be happening when you will be reaching this regime? In this regime the gas is more, so if gas is more it will occupy more space and liquid will be occupying the less space, so liquid velocity may become sufficiently high in order to achieve the continuity in the mass. Okay, so that is the reason that in case of phase change heat transfer pipeline, we will be finding that there can be significant variations at different portions in the volume fraction of liquid and vapor, and these significant variations will be significantly changing the distribution of the phases. So if distribution of the phases is changing significantly, then if I have to do theoretical analysis, then different type of formulations are to be considered for different portions of the pipeline in order to analyze it correctly. Is this point clear? So properties or parameters will not be remaining uniformly consistent. This is an photograph where convective boiling around a heated rod is shown. So you have a circular rod. On this circular rod, heat is provided from the center and it is placed in, say, saturated liquid. So you can see initially, particularly near the bottom, there is formation of small bubbles. You see all these are nothing but the small bubbles, and when we are moving in upward direction, these bubbles formation density has increased and ultimately it is resulting in formation of a formation of this vapor film. Okay.
वॉल्यूम फ्रैक्शन हमेशा मतलब लेंथ के लो और टाइम के लो चेंज होता रहेगा,
Yes.
तो फिर अपन उसको मॉडल कैसे?
No, with time, say if your system has entered into the steady regime, then what will happen? In this portion always you will be finding the bubbly flow. In this portion always you will be finding the slug flow.
वॉल्यूम फ्रैक्शन अपने को लेंथ के लो वो वेरी
Yes. You have to use different pipe segments to see what type of volume fraction is present in that segment. Okay. Of course, the flow will not be fully steady, like say your interface or bubble is forming only in this pattern. All these situations can be dynamic. Okay. But on the basis of global parameters like volume fraction, okay, this flow can be set steady. That volume fraction value in this zone may remain almost consistent with the time. Okay. Now this is about steam water flow in horizontal water boiler tube. Okay. So what happens in a horizontal boiler tube? Again, the saturated liquid will be entering at this point, and here I should have saturated or superheated vapor. Okay. So initially when flow will be starting, now gravity field is acting like this. Any bubbles which are forming because of the density effect, the bubble will try to stay near the top portion of the pipeline and liquid will be staying in the bottom. And once the number of bubbles has increased, these will be forming the larger bubble shapes which are typically called as plug flow regime. Okay, so here you can see this is the cross section of a plug. Then finally, when these multiple plugs will be joining, these will be forming the big slugs which are almost touching the top portion of the pipe. And after that, all the vapor which is forming, that will gets collected at the top portion, and at the bottom we will be having liquid with wavy boundary present. Okay, and from this wavy boundary there can be formation of small droplets, and these droplets can finally enter into the liquid. Okay, and after this wavy flow we can also see that the thin film of liquid will also appear because the gas fraction will become so high that it will displace the liquid. Once it is displacing the liquid, then a small thin film of liquid can be seen on the entire periphery of the pipe with gas at the core, which will be our annular flow. And finally, this annular film will also dying down completely and we will be getting saturated vapor. Okay, so this is the distribution which happens in a horizontal pipeline. Typically about the phase change heat transfer, I am not discussing all their features, how heat transfer coefficient varies, how bubble formation takes place, what is the maximum amount of heat flux which we can achieve in this scenario. Okay, how heat flux and temperature distribution varies. All these things we will discuss when we will discuss about the phase change heat transfer in detail. Okay. So one summary of flow regimes is presented over here, and this summary is typically presented in the form of the initial categorization which we have done. So initially we have categorized our flow in the form of well separated flow and well dispersed flow. So all the different regimes which we have studied, what are their applications, where these are typically observed, and under which category they can be clubbed, that we are actually seeing over here. So first let us talk about classification of separated flows. So typical regimes are film flow. So if you have a solid boundary, on this solid boundary if a liquid film is flowing, so this liquid film can be segregated from the surrounding vapor phase easily. So this is a configuration of film flow which comes under the category of separated flow, and this configuration is having applications in film condensation and film boiling. Okay, what happens in film boiling? In film boiling we have a vapor film over the heated surface, and over this vapor film we have saturated liquid. So this is a well separated flow. If you talk about film condensation, this is the surface, cold surface. Okay, over the cold surface we have film of liquid, and outside this we have vapor atmosphere. Okay, so in the applications of film condensation and film boiling, this occurs. Then annular flow. Annular flow means you have two situations, either gas at the core and liquid at the wall, or second situation can be liquid at the core and gas at the wall. Okay, so this type of situation is observed in film boiling, particularly in boilers. Okay, so
इन जो सेकंड सिचुएशन बताई आपने वो किस में होगी?
that is which gas core and liquid film,
यस
or liquid core gas film.
गैस सर बाहर होगी और लिक्विड अंदर.
Okay, so if you talk about film boiling inside the boiler tube, what will happen? Inside film boiling, this outer periphery will be purely vapor, this will be purely vapor, and here you will be having liquid. And in this film boiling inside the boiler tube, majorly evaporation takes place from the vapor liquid interface. Okay, so here there will not be any boiling from this, but boiling will take place from the, because liquid is not contacting the wall. Okay, so entire wall is actually covered with vapor, but liquid is at the center. So from this particular zone, this interface between the liquid and the vapor, your boiling will take place. So typically in this type of boiling scenario, vapor temperature is more in comparison to the saturation temperature of liquid at the given pressure. So then boiling starts from interface between the vapor and the steam. Okay, sorry, vapor and the liquid. Then jet flow. So we have so many things, like in IC engines, what we do? We have fuel injector. That fuel injector is actually spraying the liquid. So this is a liquid which is coming out of the injector, and outside what we have? Hot air present in that engine. So this is liquid jet which is present in gas. or there can be other situation that outside is liquid and gas jet is actually injected. Okay, so this type of application is observed in automation jet condensers. Then second is mixed or transitional flow regime. It means in these regimes the situation is combination of dispersed flow as well as the well separated flow. Okay, so in this regime the first regime is cap slug or churn turbulent flow. So here we know that this bullet shaped body is present, so this is a gas pocket which is present in the liquid, and this type of situation is typically observed in sodium boiling in forced convection. Okay, then bubbly annular flow, what it means? It means that I have liquid film, but within this liquid film also small gas bubbles are present and gas is moving at the core. So this type of situation is called as bubbly annular flow, and it is typically observed in evaporators which have wall nucleation. What is the meaning of wall nucleation? You have a tube, and in this tube have some nucleation site present at the wall. So from this nucleation site vapor will grow, and in the adjacent portion you have liquid film. So this vapor bubble which is generating from the wall, it will try to move towards the liquid film. Is this one clear? Then droplet annular flow. Droplet annular flow, if we have liquid film and gas at the core, and from this liquid film drops are forming and present in the gaseous core. So this is typically observed in steam generators. Okay.
So liquid से gas
Sorry.
से bubbles कैसे बनते
Okay. Not in this droplet annular you are saying. So these are not bubbles. These are, yes, droplets.
So liquid से gas में droplets आते हैं.
Yes, droplets. Liquid droplets are there. Your question is how these are coming? This is a wavy pattern. So from this wavy pattern what will happen? If wave is growing in amplitude, then it will form a lamella, and that fine lamella because of the gas shear will be splitting into the small drops. Okay. Then we have bubbly droplet annular flow. What is the meaning of bubbly droplet annular flow? That in the liquid film we have bubbles, in the gaseous core we have droplets. Okay, so boiling nuclear reactor channels, typically this type of situation is observed. Then we have dispersed flow. So one is bubbly flow, gas bubbles in liquid. This is typically observed in chemical reactors. Okay, so in chemical reactors we have to perform some reaction between the say gaseous reactant and the liquid reactant. Then what we will do? We will pass small bubbles into the liquid reactant. Why? Because if the liquid reactant and gaseous reactant are actually coming in contact in the form of small bubbles, then surface area will be increasing, which will improve their mixing characteristics and rate of reaction will be faster. Okay. Then droplet flow. So in droplet flow, liquid droplets appears in the gaseous medium, and this is typically used in spray cooling. Okay, so you have a heated surface. On that heated surface, if you have a jet of liquid which is spraying the droplets, then these droplets will penetrate through the surrounding gaseous phase, and these will strike on the surface of the liquid. After that, once these have striked on the surface of the liquid, then depending upon the nature there can be different characteristics. Okay, for example, if multiple droplets have spreaded, if surface is hydrophilic, these can spread together and form a liquid film. If surface is hydrophobic, then these can rebound back from the surface. But if our interest is to cool the surface, then surface characteristics should be such that liquid drop which is touching the surface, it should immediately spread over the surface and form a liquid film. Okay, because if liquid is in contact with the heat surface, then what will be happening? High conductivity of liquid will assist in fast removal of the heat.
Hydrophilic.
Yes. Then particulate flow. So particulate flow means solid particles are present in either gas or liquid, and this is typically used for transportation of powders. Okay. Okay, so regarding the shape of fluid particles, I will discuss in the next class.